Hello everyone. Thank you very much for watching this video. Today, I am going to introduce our work Unsupervised Deep Probabilistic Approach for Partial Point Cloud Registration. Deep probabilistic approaches for point cloud registration typically involve the following steps. The first step involves feature extraction. In this step, deep learning techniques are used to extract informative features from the point clouds. Convolutional neural networks, CNNs, or graph neural networks, GNNs, are commonly employed for this purpose. These networks can capture local geometric information and learn discriminative feature representations from the point cloud data. The extracted features are then used to represent the points into distributions. The goal is to group similar points together based on their learned feature representations. Once the points are clustered, the next step is to estimate point correspondences between the distributions of the source and target point clouds. This can be done using various techniques such as nearest neighbor search or the Hungarian algorithm. With the point correspondences established, the next step is to estimate the transformation that aligns the source point cloud with the target point cloud. This can be achieved using techniques like the iterative closest point (ICP) algorithm or robust estimators such as RANSAC. The transformation parameters, such as rotation and translation, are optimized to minimize the distance between corresponding points. Deep probabilistic approaches are suitable for point clouds with density variations. It's worth noting that while deep probabilistic-based approaches offer significant advantages, they also come with challenges, such as the need for large amounts of annotated training data and potential difficulties in interpreting and calibrating uncertainty estimates for point clouds with partial overlaps. Nonetheless, these approaches have shown promising results in point cloud registration tasks and continue to be an active area of research. We thus provide an unsupervised method to reduce the dependence on labeled data. 1. A point cloud should share an identical posterior distribution in coordinate and feature spaces, self-consistency loss function. 2. The GMMs from two-point clouds should be the almost same in their overlapped regions, cross-consistency loss function. 3. The detected overlapped regions should have the almost same clustering centroids contrastive loss function. Our self-consistency loss encourages point clouds to share an identical posterior distribution in coordinate and feature spaces. It can be directly used without using any data augmentation. Coordinate and feature spaces share an identical posterior distribution means that Sx and gamma x should be equal, which leads to a cross-entropy loss. The described self-consistency loss only encourages the learned representation to be spatially sensitive, but it cannot ensure that the learned features be transformation invariant. Therefore, we introduce a cross-consistency loss to encourage the network to learn transformation invariant feature representations. Our cross-consistency loss is based on the fact that the cluster labeling should not change if the points are rigidly transformed. This fact means that if points PS and PT belong to the same cluster, they should share the same cluster centroid. Therefore, the cross-consistency loss can make full use of the information from both aligned point clouds. The local neighbors provide essential information for feature learning on the objects of the point clouds. If the network captures the local structure information from other complete objects, it can boost the model robustness on incomplete objects during training. While the local descriptors of the point clouds mainly derive from the points and their neighbors, which motivates us to model the local information of the point cloud by introducing local contrastive loss. Specifically, given a centroid of point cloud Px, we search its nearest point Pxi and associated feature vector Fxi by the pointwise Euclidean distance. Based on this, we construct the local contrastive loss LLC following info NCE by pulling Fxi close to mu xi, while pushing it away from the neighbor vector of other points. We also encourage same categories share the similar cluster center between two-point clouds. This is the whole framework. Our method uses shared weighted network extracts point-level features Fs and Ft, overlap scores Os and Ot from point clouds Ps and Pt, respectively. Clusterhead consumes Fs and Ft to calculate probability matrices Ss and St, which are applied to estimate the parameters of GMMs. Next, cluster level and point level matching modules estimate the correspondences M, which are used to estimate the transformation T. The network is trained using local contrastive, self-consistency, and cross-consistency losses. S is the concatenation of S's, and Saint P and F are the concatenation of PS and PT, and FS and FT, respectively. We conduct extensive experiments to evaluate the performance of our method on the real datasets 3D match and 3D LO match, as well as on the synthetic datasets ModelNet and ModelLoNet. We chose supervised state-of-the-art, SOTA, methods, OMNet, FCGF, D3 feet, SPINIT, Predator, REGTR, CoFINet, and GeoTransformer, as well as unsupervised PPF FoldNet and SGP as our baselines. This table reports the results on both 3D match and 3D LO match datasets. This table reports the results on both ModelNet and ModelLoNet datasets. Example: qualitative registration results for 3D LO match. The unsuccessful cases are enclosed in red boxes. Registration results of different methods on ModelLoNet with more than 50% partial overlaps. Thank you for your listening. We will release our code.